This section, we're going to go over backpropagation, which is how neural networks learn. Cool. So we learned about forward propagation and how the inputs to our neural network can be mapped to our output. And, as with any kind of machine learning model, we can use a loss function to evaluate the current set of parameters and then update it. And as a refresher, right, a neural network's parameters are going to be the weights and biases between any two nodes within our neural network. And after we evaluate the loss function, whatever that might be, we need to update the weights. But doing this is not as intuitive as you think. For example, right, if we have a loss function, which is going to be a function of the predicted output as well as the ground truth target, we want to use whatever loss we get here to update the weights for, say, this specific connection all the way back in the input layer. And doing that is not the most intuitive to think about, right? How is this loss going to affect the weights all the way back here? And to sort of wrap your head around how this might work, we need to first do a refresher about forward propagation, which we covered 2 sections ago. Which, as a refresher, for a given input vector x, we can generate a prediction using a chain set of matrix operations, essentially, right? Where if layers 1's weight is represented by a matrix W1, our function f of 1 will take these two, this vector and weights, and essentially take the weight sum, right, apply the activation function. And the fact that this output becomes the input to the next layer allows us to chain all of these functions together, right? Where f of n is going to be the function that maps the last hidden layer's output to our actual prediction. Using this fact, we can essentially use the chain rule, which you might have learned about in your multivariable calculus class, to compute the gradient for any set of weight, wi. More specifically, the gradient of the loss function with respect to the weight in any layer I can be represented as the gradient of the loss function with respect to the last layer's output times the gradient of the last layer's function with respect to the previous layer, all the way on and on until we get to the weights for the layer I of our interest. And the reason why this works is because we might not know how this loss function directly affects the weights all the way here, but we do know how this loss function is going to be affected by making tiny changes in the parameters in our last hidden layer. Also, we know how the inputs or the outputs to our hidden layer is going to be affected by the weights in the layer before that, right? So we might not know the direct impact of our loss function to any set of weights, but we do know the marginal contribution that one layer is going to make to the next. And using this logic, right, we can then basically chain all these gradients together until we reach a layer of our interest, right? And once we are able to obtain this gradient, we can then, use a simple, gradient descent algorithm to update the weights, right? So the new weights for layer I is going to be the old weights Wm minus, some learning rate R times the gradient of our loss function with respect to the current weights. To sort of summarize what we just learned, it is generally good practice to try doing a round of forward propagation and back propagation by yourself. So I recommend you guys to do this. I'm not going to make this mandatory, but for the given neural network below with these configurations, you can try and take like a minute, right? Get a pen and paper out and try and do a single forward propagation through this network and assume that the hidden layer in the middle is going to use a ReLU activation function and that the output layer uses a linear activation function. Okay. Once you're able to do this, we can sort of go over the answers here. So we have our input 1058, right? That's our input vector. And we also have our network weights, right? So we have for 10, 1, and -2. We also have -1 and 2, right? -1 and 2, and also 2 and -2, which, I didn't make a paper, this should be 2 and -2. But if you, multiply W1 x, this gives you the weighted sum here. Applying the ReLU function gives you the output to our first, basically the values of our first hidden layer, which is going to be 0 and 6 here. Then, this becomes the input to the next set of layers, right, and connections, where we can use the weights -1 and 2 here to essentially get our output 12. And if we assume that, the ground truth value is 14, then if we use a mean squared error loss function, then, our loss is going to be 4. And assuming that the learning rate is equal to 0.1, we can now, do basically around a back propagation, where essentially the weights we want to update is going to be W1 and W2. And to update W2, we can just take the gradient of the loss with respect to, the function F2, and take the gradient of F2 with respect to the actual weight of our interest. And we can do the same for W1, which is going to be, these set of weights in our first layer. Cool. Now that we have a mathematical understanding of gradient descent and propagation, let's try to implement this in PyTorch. So for classification, right, which is the task that we're doing with digit classification, we mainly want to use cross-entropy loss. And in PyTorch, we can use nn.cross-entropy loss, which conveniently implements this for you. One thing to note is that the cross-entropy loss function expects raw logits as inputs. It actually computes the softmax for you internally, which is why when we defined our model architecture two or three sections ago, we didn't actually add the softmax activation function at the end, because our loss function is going to do that for us. And if we do include it in our model architecture, we're essentially going to be computing softmax twice, which is of course wrong. Another thing to sort of define before you go into model training is an optimizer. And an optimizer configures the exact, back propagation process of a model, right? So it defines the specific algorithm you're going to use for backprop. It defines key parameters like the learning rate, L2 regularization, momentum, etc. Some famous optimizers include the stochastic gradient descent algorithm, which is basically the one we've been covering in this workshop, as well as the Atom algorithm, which is a more modern approach used in a lot of deep learning methods. For the sake of simplicity, we're going to be focusing on stochastic gradient descent. But do know that both of these algorithms are very commonly used as optimizers to a deep learning model. Let's go over some key parameters to PyTorch's SGD function. The first key parameter is the actual parameters to your model that you want to update. And to basically input this, it's very simple. You just do your model name dot parameters, right? So whatever you define your model as using n.sequential, right? That variable name dot parameters is going to give you the set of parameters that you want to update. Other key parameters that are worth configuring is the learning rate for your model. 0.001, which is the default value, and also 0.01 are always like a safe middle grounds to get started with. There's also momentum, which essentially is a factor that allows you to escape local minimums. Essentially, when you think of a loss function, there might sometimes be local minimums, right, that are not actually like global minimums. And to make sure our model optimizes properly, we want to be able to escape them, right? We don't want a zero gradient to make us stuck at a local minimum and not a global minimum. To do so, we can basically borrow the weight update from our previous iteration and apply that to the current weight update, so that if we ever reach a state where the gradient is close to 0, then our momentum will allow us to escape that thorough, right, or that local minimum. And the exact value of our momentum dictates how much of the previous weight update we want to factor in to the current state. And generally speaking, 0.9 is a good place to get started. There's also weight decay, which defines the L2 regularization penalty. And this factor helps you prevent overfitting in your model. by essentially simplifying the parameters to your model. And a good place to get started is to set the weight decay or the LT regularization to 1e minus 4, which is just 1 times 10 to the power of negative 4. And one thing to note is that the higher this value is, the more you penalize overfitting while sacrificing accuracy of your model. Cool. Now that we define our loss and optimizers, we can actually go ahead and train your model. And training a model in PyTorch isn't a simple fit call like a second lane, but it's pretty straightforward. And there's a set formula to use. And we're going to go over this recipe for training a model in PyTorch here. First, as I said before in the previous section, you want to define the maximum number of epochs you want to train the model for, right? You can also add early stopping criteria too, but the number of epochs sets an upper boundary of the number of passes through an entire data set that you want to train your model for. Then you want to write a for loop in Python where you loop through every epoch, and for epoch, you load a batch of data from our data loader object that we defined before, right? And each of this, batch of data is going to have, n samples, where n is the batch size that we defined. And after we load our data, there are 5 steps we want to take. First, we want to clear the gradients that we've accumulated from the previous step or the previous, weight update by calling optimizer.zeroGrad. Then we want to get the model predictions for the current step data by doing outputs is equal to model inputs, right? And that just basically does forward propagation for you. You can then compute the loss by simply calling the loss is equal to whatever you define your loss function as, right? And as the input to your loss function, the outputs, which is the predicted values from forward propagation, and then targets, which is the ground truth value that you get from your data loader. Then, after computing the loss function, you can do back propagation by doing loss step backwards. And this is essentially going to compute the gradients, right? Much like what we did here. And then after computing all the gradients, we're going to update the weights using these gradients using optimizer.step, which basically allows you to take a step towards the local minimum. And by repeating these 5 processes for every batch of data and for every epoch in our model training, we can then converge to an optimal set of parameters. Cool. So as our last exercise, go back to our notebook and then actually complete the for loop. So I actually wrote a lot of the for loop for you. So if you go to task 3, you can see that I actually tried implementing for loop over epochs and for loop over the train data loader. But your to-do is to essentially replicate these 5 steps in this section of the for loop. And since this is your first time working with this, I've defined most of the for loop for you, but try and read through the code, understand it so that you can write it from scratch by yourself in the future. I'll give you guys 3 minutes to work on this and pause the video now. And when you're ready, we can go over the solution. I hope you've had a chance to go over the code. And we're going to work through the actual answer right now. So our code basically loop through every epoch and enumerate over a train loader, which gives us the batch index that we're working with within our data set, as well as the inputs, the input vector, and the targets, which is our ground truth, target variables. And each of the code here is going to be commented for you, right? Essentially, each batch has, n samples where n is the batch size, and we can add, targets.size 0 to the total number of examples that we've been evaluating. We can afterwards, it's very important actually to flatten our tensor from batch size 12828, which is the size of our input, to batch size 784, which is the flattened version. And you can use this by using the view function. Afterwards, we're going to put the tensors to the device. And then here is basically the replication of the 5 steps that we sort of went over here, right? So the first thing is we want to, zero the gradients, clear the gradients. Then we want to do a round of for propagation. We want to then, compute the loss function, which, if you recall from here, we define our loss function as loss fxn, right? So this is the loss function that you should be using. And the input is going to be our outputs and targets, right? Our outputs is the prediction from our for propagation, and the target is our ground truth. Then, we can do backprop with loss set backwards, and then actually update the neural network parameters doing optimizer step. And the rest of the code, it just essentially adds to the running total of the correct number of examples, right? By comparing, how many samples, right, in our batch did the actual prediction, right, equal targets. And the reason why we use argmax is because essentially, if our prediction is a set of 10 probabilities, we want to find the probability which is the highest, right? And the index for that is going to be our predicted value. And here we're just essentially logging the loss at a certain interval. If you actually run this set of code, you can see that we're actually running our training loop, right? And you can see that the loss, gradually sort of decreases. And, as a little brain teaser, it would be, good practice to try and think about like where these numbers are coming from. Like, why is there 6,400 and why is there 60,000 here? Um, you see that our training accuracy between this epoch and this epoch definitely increased. Maybe I set the learning rate to too low. But yeah, so we have a train accuracy of 0.9277. If you run this code below, you can see, how our model still learns over time, where this is going to be our cross entropy loss, and this is going to be the number of training batches that our model saw. You can see that, it's not really a smooth decrease. And this is, of course, because we're not using batch gradient descent, right? We're going to be taking more erratic steps towards the minimum. And, after, you train your model, you can actually, evaluate on your model on the test set. And some key things to note is that when you do model evaluation, it is very important to do two things. First, you want to switch your model to evaluation mode by doing model.eval. Switch back to train mode, you can do model.train, or maybe not. The model.eval basically switches the model to evaluation mode. And with torch.nograd allows us to make sure that we don't actually compute gradients when conducting inference, right? So whenever you do inference, make sure you run these two lines of code, or you have that in your inference code. You run this, you can see what our accuracy is on our test set, which is 0.9350, which is not too bad. There's some bonus exercises for you to work through as well. But yeah, that sort of concludes the training script. And that concludes it for the workshop as well. Hope you learned well, and I'll see you next week for our sort of lectures on convolutional neural networks, which essentially allows us to solve this digit classification task and more complicated computer vision tasks more efficiently.